We're continuing in 2.8 with Theorem 4. If f is differentiable at a, then f is continuous at a. So, not proving this theorem or anything is something we're going to use later. It's just introduced in this section. We say differentiability is a stronger condition of f at x equals a than continuity, meaning that we do have f is differentiable, then f is continuous, but if a function is continuous, it's not necessarily differentiable. So a little example to show that is our friend y equals the absolute value of x at x equals 0. We know, and we talked about at a corner, which is what we have here, that the function's not differentiable there, but it obviously is continuous. And so that's an example showing where you have continuity but not differentiability. So just something that we'll use later on that's in this section. So mostly I want to go over this example 1 here. Find the derivative of f of x equals x minus x squared. Then evaluate f prime of negative 1, f prime of 0, and f prime of 1. So just an aside here that this is the same y equals f of x from example 1 and 2.7. And we're asked a slightly different question here. For that one, we were finding in particular the derivative at x equals negative 1. Here it's just saying find the derivative of f of x to start out, which means we need to use this f prime of x, limit as h goes to 0 of f of x plus h minus f of x over h definition, and leave x as a variable instead of plugging in a particular a value. Then evaluate these other things, which we'll do after the fact, and it'll be way easier to find that. So if you want to find multiple derivatives of a function at different values, then it definitely makes sense to find what it is as a function and plug in later, which is what we'll see here. So getting back to finding this derivative as a function, limit as h goes to 0. And now, just like when we plugged in x plus negative 1 or something like that, we're going to do the same type of thing, but it's going to be x plus h replacing all the x's in f of x. So you might want to put some parentheses here to see it wherever there's an x. X minus x squared, or parentheses minus parentheses squared, and what f of x plus h means is inserting x plus h in those parentheses. Do not just attach a plus h at the end, that's not what it is in general. Minus f of x, which I need some parentheses here around the x minus x squared. That's all over h. Now the catch with this definition, because it's more general, our algebra is going to be really similar to when we had a plugged in x equals a specifically, but it's going to be more complicated, a little bit more work, so that's the trade-off for it being more generalized. So first step, if you try plugging in h equals 0, you will get 0 over 0, so you can just skip that step. It's going to always happen. Expand the top. There's a hidden factor of h on top, and we'll discover that hidden factor if we simplify. So x plus h squared, be really careful. You cannot just bring in the square when it's plus or minus on that side of those parentheses. There's no property that allows you to do that. So you got to expand that out by FOILing out x plus h times x plus h. And you get x squared plus 2xh plus h squared. I'm going to distribute the minus here. I get minus x plus x squared. That's all over h. Do some more simplifying. Limit as h goes to 0. Got to distribute this negative here. Notice the x's from that right here will sum to 0. So I have h minus x squared minus 2xh minus h squared plus x squared all over h. Simplify on top, negative x squared plus x squared is 0, and that's it. So now when you've done this correctly, which I have, you will have a GCF of h on the top. If you don't, you messed up, but don't fake it. Go back and figure out how you screwed up and show correctly how to do that algebra to get to that point. So factor out that h, you're left with 1 minus 2x minus h. Cancel with the h in the denominator. We're not going to get 0 over 0 anymore. We substitute in our h equals 0 and we get 1 minus 2x minus 0, which is 1 minus 2x. Now that may seem weird, but remember that we were finding the derivative as a function, so the fact that we have an x left in it is a normal thing. We do have constant functions like y equals 2 and stuff like that, so if you don't get an x in there, it doesn't mean it's wrong necessarily, but usually we get an x in there. That was the first part. Now the next part is to just find f prime of -1, and you don't have to go back to 2.7. You have this nice nifty little equation now for the derivative function. So just plug that in like you would any old function where you put in a -1 for x. So I have 1 minus 2 times -1. So do that and you get 1 plus 2, which is 3. And that's the answer we found from 2.7, example 1. This is a harder way to do just the derivative at x equals -1, and it should be mentioned that if you are just trying to find the derivative at a equals -1, for example, for this function, 2.7 is the way to go because it's easier. But if you're told to find the derivative in general, you need to do that. But also, if you're told to find the derivative at lots of different places, then getting this formula is the way to go, because now it's super easy just to plug into that formula and get all these derivatives instead of doing them all from scratch. Okay, this was not one of the ones I was supposed to find, but I'm going to throw it in here because I want to show you the graph and what that means. So we got lots of derivatives here at different values of a. So this graph up here, I'm just going to grab it for a second and bring it down. Let's go back to the meaning of the derivative. Oops, sorry. Straight down here, I guess. So for all these particular f prime of -1, f prime of 0, we can bring that back to what that meant when we first talked about it. And so at -1 for our x value, it's kind of off this graph a little bit, maybe right here or something, it's talking about the slope of the tangent line, and that slope is 3 exactly at x equals -1. At 0, we're talking about the slope of the tangent line at x equals 0. So the slope of that line is exactly 1, which matches the picture. I threw in the 0.5 because we got 0, which means there's a horizontal tangent line here. And then finally f of 1 is about right here, and the slope there is -1 for that tangent line.